I think, yeah, like I think my most liked video I think is like 5 or something like that. Hello and welcome back to our Wednesday lecture. We're gonna pick up where we left off on Monday, as always. But before we do, I want to take a moment and talk about the exams, because both are closed. So I have statistical information on both the prerequisite exam and exam 1. Now I know that Canvas displays some statistical information for you, but one thing that you don't have is statistical information spanning both sections. Remember, we are, or I am, I should say right now at this moment in time, teaching there's 2 lecture sections worth of students who are taking Chem 400 from me right now. One section is mine. That's the one that has like 16005. And then the other section, the 15 something, I don't remember the last 3 numbers. That's actually Professor Mahoney's section that I'm covering the first half of the semester for him while he's on paternity leave. So for these first few exams, I actually have, when you look at the stats, when you display the average, it'll only show 1, but I get to look at both, and so I can look at an overall average, so we can get an average over the 100 students enrolled between the 2 sections. So the prereq exam had an average across both sections of 73.5%, and exam 1 had an average across both sections of 71.5%. And so looking at these numbers, I've only just started to kind of break down the stats and look at things. Standard deviations are looking solid. They're around 10-ish, which is good, where they should be. What usually, and again, I'm going to do a deep dive into both of these, but usually this is actually high for prereq exams. Most prereq exams that I give have lower averages, but usually this means that there's some sig fig work that needs to be done. But when I look at my exam 1 averages, an average of 71.5 is pretty solid. All right, so collectively, I would give yourselves a high five, give yourself a pat on the back, because that's a decent chemistry average. It's not uncommon in STEM classes, especially chemistry, to see averages that are lower in the 60s, and so we managed to all together hit a 71.5, which is pretty solid. A couple things that I wanted to mention before going on. I have received several emails from you who are concerned. I've started replying, but I haven't got around to replying to everyone yet. So if you haven't heard from me yet, you will be. It's every time an exam closes, there's always like an avalanche of emails, and so I'm working on getting responses out to everyone. Kind of what I do is I like see, okay, look at all the emails, kind of skim through them, and then start replying to them all systematically. So I'm in the process of doing that. One concern that I've heard voiced by a few of you was one of time, and not feeling a time crunch, feeling like there wasn't enough time, etc. And what one of the things that I have to say about testing in Canvas is the problem types that I can write and implement in the online testing format limit the complexity of the problem. When we're teaching in person, when I'm teaching in person, you know, and you roll in, you take the exam over a class period. My exams typically have anywhere from 5 to 7 problems on them, because in class I tend to write these kind of complex, dense word problems and have you unpack them. You like have the text up at the top and then the page to work it out, to do your calculations, to show your work and all that stuff. Whereas in Canvas, when you're testing online, there's no way to do that. And so the problems tend to be shorter as a result and less complex. So the form of testing that Canvas takes is tend to be shorter problems, simpler problems, and just rapid fire. And part of the testing format is a time constraint. So I would not anticipate the time pressure changing in the future. I wouldn't anticipate it ramping up or getting worse, shorter. But the amount of the time pressure for future exams will be pretty much at the level of exam 1. And now that you've been through exam 1, you should use that to inform how you study, because you want to get comfortable with these problems so that you can just whip them out, solve them very quickly. Also, test-taking strategies, you should skim the exam, find the ones that are easy, find the ones that are quick, and knock those out first. If there are problems that take longer calculations, you should be saving those for the end. All right. So I wouldn't expect time pressure to change on future exams. It'll be roughly the same moving forward. So with that being said, I know the focus was on the test, right, which closed on what was it, on Monday. But something to keep in mind that you should keep in mind is we have our second E-Lab coming up. Everybody's due dates may be different, right? Because we have 3 different lab instructors and each one sets their own schedule. I know my section is due on Monday, which is, pulling up my calendar, the 28th. Monday the 28th. And tonight, I'm going to be doing a mini lab lecture at the start of open office hours tonight. So if you want to tune in, I'm going to kind of be going into kind of the conceptual background, what this thing's all about. Or if you don't tune in, but you're rolling around, if you're starting this thing on maybe next Monday night, as I know some of you will, you can remember like, oh yeah, he had a mini lab lecture, and you can go and watch that. So that'll be there for you. I'll be doing that tonight. Okay, so that is all I wanted to say about that at the moment. Let's go ahead and resume with our discussion of precipitation reactions. All right, and so we left off in lecture on Monday looking at this precipitation reaction, and what makes it a precipitation reaction is this solid. This solid product is the precipitate, and that is the definition of a precipitation reaction. You mix 2 aqueous solutions, and at least one of the possible products, is a solid, a insoluble ionic salt, as is lead to iodide. All right. Now, I want to take this example and use this example to introduce two new ways of writing chemical equations, or two new types of chemical equations. All right, because you'll notice, and as I've underlined, we have three aqueous species in this reaction, and we know that when you have an ionic compound that's in the aqueous phase, that the ions, the cation and anion, dissociate. They don't remain associated when dissolved in water. They're separated by the solvent. And so another way you could write this reaction is with every aqueous ionic pair separated. So this could be written as lead 2 cations plus nitrate, aqueous nitrate anions, right? Coming here from the reactant lead 2 nitrate, here and here. One thing you'll notice though is there are 2 nitrate anions in one molecule of lead 2 nitrate, so we would need to give nitrate a stoichiometric coefficient of 2. All right. Plus, now let's go ahead and break apart potassium iodide. So this would be plus aqueous potassium cations and aqueous iodine, or iodide, excuse me, anions. Now, even though there's only one potassium and one iodine in this chemical equation, we had in that chemical formula, excuse me, we had 2 of those molecules in this reaction, so both of these will get a stoichiometric coefficient of 2. All right? And now our products, onto the product side. We have our next aqueous ionic compound to write out is potassium nitrate, so we have free-floating aqueous potassium ions plus free-floating aqueous nitrate anions. And again, because we had 2 of these molecules, we have to put a stoichiometric coefficient of 2 in front of potassium and nitrate. And then finally, we write plus Pb I2. Now, the important thing to remember is when you have a solid product, as we do here, it remains associated. You only are breaking apart compounds that are in the aqueous phase. So you'll notice that we have 3 aqueous ionic compounds, and these are the ones that we split up into separated cation and anion pairs. But if an ionic compound is solid, that means it's insoluble in water and will remain associated. All right, so this whole thing right here, I'm actually going to bump this down. There's a name for the this type of chemical equation where we separate out all of our soluble ionic compounds into their separated cation and anion pairs. This is called the total ionic equation. All right, this is our total ionic equation. All right, now I want you to notice something within the total ionic equation. All right, I want you to notice something. I want you to notice that on the reactant side, we have, let's see. Jared, great question. All right, so Jared just asked that he said we just don't separate the polyatomic ions and the solid part, right? And that is correct, because the polyatomic ion, like nitrate is in this reaction, is a unit. It is an ion together. It is an ion that's made up of 1 nitrogen, 3 oxygens, and has an overall negative charge. So you never break those up into their elements. The polyatomic ions stay together because they're a unit. They're an ion as a collective. So keep those all together as ions, and then keep the solid ionic compounds together and associated with each other. All right. Now notice something. We have 2 potassium cations on the reactant side, and we have 2 potassium cations on the product side. Also, we have 2 nitrate anions on the reactant side and 2 nitrate anions on the product side as well. And you'll notice that they're unchanged. They're all in the aqueous phase. Their phase doesn't change. The quantity doesn't change. And because they don't change, that means they don't actively participate in the chemical transformation of this reaction, and they get a special name. They're called spectator ions. They're called spectator ions because they're there and they're just watching the reaction. They're not participating in it, all right? They're like the crowd at a sporting event, right? Although it's a bad analogy in 2020 because any sporting events that are happening don't have an audience. So imagine in the before times when you could go to a basketball game or a football game or a whatever sports ball of your choice was, and you could be part of the crowd. You were a spectator to that game, just like these ions are a spectator to the reaction, and the total ionic equation displays everything in all its glory. That being said, the net ionic equation if you were asked to write a net ionic equation to do so, you would have to exclude all the spectator ions. In a net ionic equation, there are no spectator ions. All right, no spectator ions. So, if we wanted to write the net ionic equation, it would look like this. We would only include ions that are not spectating. So lead 2, 2 iodides, and then our solid product. So the net ionic equation would simply be Pb2 plus aqueous plus 2 iodide anions, also aqueous, producing lead 2 iodide solid. And this would be the net ionic equation. So you have a chemical equation, or sometimes it's called the molecular equation, which is the normal kind we've been dealing with. In the total ionic equation, you separate your soluble ions into their separated cation and anion pairs, and then in the net ionic equation you cancel all your spectators, and you're just left with only the reactants that are participating in the reaction. The difference between the total ionic equation and the net ionic equation are simply the net ionic equation is when the camera at a basketball game hammers in and just shows the players on the court. You're just watching the players. Whereas the total ionic equation is kind of those sweeping wide-angle shots where you see the entire arena filled with people, or empty as is the case this year, where you see it all, including the game and the people not playing the game. The net ionic equation zeroes in on just the chemicals that are reacting, just the players, not the audience. All right? Okay. So that is the difference between a molecular equation, which is just a normal one, total ionic equation, and net ionic equation. All right? Now, We'll be doing more of this in the future, but we have a more pressing question at hand at the moment, and that is, how do you tell if a precipitation reaction is even going to occur, right? I was able to write that reaction out because I knew that lead 2 iodide was insoluble in water, but the question is, how do you know when given two aqueous compounds if they're going to react and produce a precipitate? And the answer to that question comes in with the solubility rules. All right, the solubility rules. I would recommend that you memorize these, or at least, if you're not going to memorize them, have them on a note sheet when you take the exam, so you can look at them for quick reference. All right. So these are the solubility rules. I'm going to give you 4 categories of ions. Always soluble, usually soluble, so that is soluble with some exceptions, usually insoluble, right, which is going to be insoluble with some exceptions, and then always insoluble. All right. So these are the 4 categories to look at. First, always soluble. Our list of always soluble anions and cations are as follows. Lithium, sodium, potassium, and ammonium. And then, in addition, there's also, those are the cations, and then nitrate and acetate. These ions are always soluble. Okay, Angelina's got a question. So if a compound is aqueous, that means there's water, but we just don't put the water in the equation. An aqueous compound is actually ions and not a compound. Okay, Angelina, great question. For aqueous compounds, water is the solvent. It does not have to be the reactant. All right, sometimes it will be a reactant or a product, but it doesn't have to be. It just means that everything that's reacting is dissolved in water. And then an aqueous compound, okay, so the second point that you make, where you say an aqueous compound is actually ions, not a compound. An important thing to note. Aqueous ionic compounds are dissociated ion pairs. All right, covalent compounds are just covalent compounds. They don't break up in water because they're not a cation and an anion together. But aqueous ionic compounds, that is correct. They don't stay together. They just float apart in solution. So aqueous ionic compounds. All right, these are always soluble. Now let's talk usually soluble. These are, I don't know why I put an E. These are ions that are soluble with some exceptions, all right? And they are chloride, bromide, and iodide, Actually, but these are insoluble when you pair them with either silver, Mercury 1, or lead 2. All right, so chlorine, bromine, iodine, soluble with anything except silver 1, Mercury 1, and lead 2. All right. Another ion that is usually soluble is sulfate. But sulfate is usually soluble, but it's insoluble with strontium, barium, lead 2, silver, and calcium. All right, a little bit larger rogues gallery for sulfate. Sulfate is soluble with almost everything, but not these 5 ions. All right, so it's our always soluble, our usually soluble. Let's talk about usually insoluble. Ions that are usually insoluble. Ions that are usually insoluble are calcium, strontium, and barium. These things are insoluble with just about everything. With the exception, these are soluble with sulfide. I need to clean this up just a little bit. These are soluble with sulfide, and they are what's called slightly soluble. Slightly soluble with hydroxide. All right, now what does that slightly solubility thing mean? All right, for this class, we're just going to treat our slightly soluble compounds as if they were soluble. All right, we're just going to treat our slightly soluble compounds as if they're soluble. Slightly soluble compounds kind of dissolve, but they have a hard time doing it. So often if you make a solution, for example, with calcium and hydroxide, calcium hydroxide solutions are notoriously cloudy, and it's because the calcium hydroxide doesn't totally dissolve. It's not an insoluble salt. It's not sitting there on the bottom as like a solid, but it's also not going fully into solution either. You will explore this concept of the kind of middle ground between totally soluble and insoluble in second semester Gen Chem, Chem 401. So you will be getting a greater taste of this when you start looking at solubility products and all that really, really, really fun stuff. This semester we're going to keep things simple, okay? So we're going to treat it as if they're soluble, but I wanted to mention that technically it's not pure solubility what we're talking about, but you're still going to write them just in the aqueous phase. And you'll see them written in the aqueous phase. So I don't want there to be a confusion. I wanted to just make that clear distinction. All right? So that is the usually insoluble anions, and now we have the straight up insoluble anions, which are carbonate, always insoluble, phosphate, always insoluble. All right, so this is kind of the reference sheet. If you're looking to make a reference sheet to use on exams, on quizzes, this is the one you want to make. This is the one you want to reference while doing homework. But before we start applying this, I need to point something out. Oh, I just wrote insoluble. I should write. Oh, here. That's sloppy. Gonna scoot this over just a little bit. There we go. This is one of the things that I come to appreciate about distance learning is my whiteboard is infinitely more forgiving until it crashes than my normal one. All right, always insoluble. What happens when you mix an always insoluble anion with an always soluble cation? Right? If these cations are always soluble and these anions are always insoluble, when you mix them, are they going to be soluble or insoluble? Well, the same thing happens when an unstoppable force meets an immovable object. All right? One of them's got to give. One of them's got to give. And in this case, the good guys win. Solubility wins in the end. If you pair an always soluble with an always insoluble, all right, if you do that, the result will be aqueous. All right, solubility will win in the end. Same thing will happen, and this is worth noting, it's the same for always soluble with usually insoluble. All right, the always soluble will always be soluble, and they trump the usual insolubility and the always insolubility of the other groups. Okay, so honestly, whenever I'm doing these problems, I always look for my always soluble anions and cations because those ones are quick answers. All right, those problems resolve themselves the fastest. So let's, now that we've seen the solubility rules, let's take some time to apply them. Let's take some time to practice. All right. So for the following problems, all of these are going to have the same set of rules. Determine if a precipitation reaction occurs if it does, write a balanced chemical equation and a net ionic equation. All right. So for each of these examples, we are going to determine if a precipitation reaction occurs. Then, if one does, we're going to balance the chemical equation and write a net ionic equation. Our first example is when you mix aqueous lithium iodide with aqueous barium sulfide. And that's all I'm going to give you. Here's the cool thing about precipitation reactions. I don't have to give you the products because you already know how to figure out what they'll be. All right? So here's how we do it. We know that if a precipitation reaction occurs, what's going to happen is our first cation is going to grab our second anion, and our second cation is going to grab our first anion, right? So our products will be lithium sulfide and barium iodide. Now we need to determine what those products will be first. Lithium's a cation with a +1 charge. Sulfide is an anion with a -2 charge. So lithium sulfide will be Li2S. Plus, now we have barium, which is a cation with a +2 charge, and iodide, which is an anion with a -1 charge. So barium iodide is going to be Ba(I)2. All right. Now we have to determine what the phase is going to be for both of these. All right. If one or both of them is a solid, then we have a precipitation reaction. We have more work to do. If both of them are aqueous, no reaction occurs. So we just say no reaction and move on. All right. So let's look at the first problem, or the first compound. Lithium is always soluble. All right, so that means that lithium sulfide is going to be in the aqueous phase. All right, now with our second one, looking at our solubility rules, iodide is usually soluble. All right. It's usually soluble. It's insoluble, so we need to know, okay, well then when is iodine insoluble? Iodine is insoluble when you pair it with silver 1, mercury 1, which is a polyatomic ion, or lead 2. And since barium is not on that list, that means that barium iodide will be aqueous. It will be soluble in water. All right. It doesn't matter now if you're going, wait a minute. Okay, so yeah, never mind. I'm not going to say what I was going to say. So, because both of the products are aqueous, there is no reaction, and we don't have to do any more work. No reaction, we're done. This can be confusing for some students because you may be looking at this and going, Josh, this looks like a reaction happened to me. It looks like a reaction happened. And I'm going to take a moment to show you why it isn't, okay? To show you why no reaction happened. I'm not going to do this for every problem that we hit no reaction, but I find it's useful, it's helpful when we look at the first one. So, for a moment here, so I'm gonna balance the chemical. Whoa, that doesn't balance it, but this does. Throw 2 in front of lithium iodide. Now we have 2 lithiums on each side, 2 iodides on each side, 1 barium, 1 sulfide. So this is the balanced chemical equation. Watch what happens when we write the total ionic equation. Cameron, great question. You only have to balance if a reaction occurs. Yeah. Totally. I'm balancing this one for illustration purposes to show you why no reaction occurs. Oh, hang on. There we go. Okay. Photoshop decided to temporarily freak. So I'm just adding in our phase symbols again. Watch what happens when you write the total ionic equation. We have 2 aqueous lithium ions plus 2 aqueous iodide ions. Dude, you are totally welcome. Plus barium plus sulfide. And this reaction produces 2 aqueous lithium cations plus a sulfide anion plus a barium cation plus 2 iodide anions. All right, now take a look at this. On the reactant side, you've got 2 lithium cations. On the product side, let me get my correct charge on lithium and maybe put a charge on iodine, I don't know. There's 2 lithium cations on both sides of this reaction. There are 2 iodide anions on both sides. 2 barium cations, 2 sulfide anions. In other words, nothing changes. There is no change, which means there is no reaction. And this will happen every time you have 100% aqueous ionic compounds on the reactant side and 100% aqueous ionic compounds on the product side. All right. Now, I'm not going to go into that full breakdown on every problem in the future, but this is why. When everything is aqueous and ionic, and you write the total ionic equation, both sides look identical, which means no change has occurred, which means no reaction has occurred. Okay, let's do another example. Let's determine whether or not a precipitation reaction occurs. And if it does, we'll balance and write a net ionic equation for the reaction between aqueous potassium chloride and aqueous calcium sulfide. All right, now we know how this is going to go down. Potassium grabs sulfide. Calcium grabs chloride. Now let's take a look at all of our ions. Potassium is a +1. Chloride is a -1. Calcium is a +2. Sulfide is a -2. So calcium sulfide will pair up as K2S with some phase that we haven't determined yet, and calcium chloride will show up as CaCl2, again with a yet to be determined phase. All right, now, potassium is always soluble. That means that it doesn't matter what it's paired with, it's automatically aqueous. Chloride is usually soluble. And again, we've got to remind ourselves what it is insoluble with to see if this will be a solid or an aqueous compound. It is insoluble when it's paired with silver 1, Mercury 1, or lead 2, because calcium is not on that list. Calcium chloride is aqueous, and therefore we have no reaction. No reaction occurs because both potential products are not products at all. They're just in the aqueous phase. All right. Now you may be going, okay, his first two examples were no reaction. The third one's gotta be precipitation reaction, and that might be true. We're about to find out. But the reason why I open with two problems that are no reaction is so you know going in that you should expect there to be problems with no reaction on the exam. I'm emphasizing it in lecture, you should expect it on exam too. So don't be surprised, and don't second guess yourself if on exam 2 you're running into problems that say predict if a precipitation reaction occurs and you're coming up with a lot of no reactions. It's going to be a problem bank, right? So you don't know how many of each are going to pull out. Everybody's pulling different numbers here. Different problems. So let's do another example. Let's determine if a reaction occurs for chromium 2 bromide, which is aqueous, and aqueous sodium carbonate. All right, now we're kind of getting into our flow. All right, we know that chromium pairs with carbonate. We know that sodium pairs with bromide. So let's write out our cations and figure things out. Now, chromium is a transition metal. We don't know what its charge is initially, but we know it is paired with 2 bromides. So if it's paired with 2 negative charges, it must have a charge of positive 2. Sodium is a cation with a charge of positive 1, and carbonate is an anion with a charge of negative 2. So if we're going to pair chromium and carbonate, that means that they're going to combine in a 1-to-1 ratio. CrO3, whoops, I started writing aqueous. Maybe I was right, maybe I was wrong, we'll have to find out. Next, we're going to pair sodium and bromide. These two will come together in a 1-to-1 ratio as well. NaBr. We don't know that phase either. So let's take a look. Sodium, always soluble. I always hit those first because they're fast and easy. If you can know to identify them, even if you're using a cheat sheet, right, to help you on the exams, which is not cheating because I let you do it. But if you're using one, I think it's even still worth it just memorizing your always solubles, so you can just look at things and know instantly aqueous without even thinking. All right. Okay, now this is where people get freaked out often, because if you look back at the solubility rules, chromium isn't even there. And this is where students freak out because they'll be like, this is an impossible problem. He never talked about chromium. How am I supposed to figure this out? If you find yourself feeling those panicked feelings, take a deep breath and look one ion over. If I've never talked about one of the two ions in an ionic compound, then dead to rights, I did tell you something about the other one. And carbonate is always insoluble. All right? As we discussed, the only thing that can make an insoluble ion soluble is if you pair it with one of the always solubles. So this is always insoluble, which means that we have our first precipitation reaction. Chromium carbonate is a solid. All right? Because we're dealing with an actual precipitation reaction here, we need to do the part 2 and 3 of this problem, right? We need to write a balanced chemical equation and a net ionic equation. Step number 1 in this game is going to be balancing, right? So let's go ahead and make an atomic inventory. We've got chromium, bromine, sodium, carbon, and oxygen. Dang, we got a lot of elements up in here. Chromium, bromine, sodium, carbon, and oxygen. So on our reactant side, we have 1 chromium, 2 bromide, 2 sodium, 1 carbon, 3 oxygen. On our product side, 1 chromium, 1 bromine, 1 sodium, 1 carbon, 3 oxygen. So we need to balance sodium and bromine. We can do that if we multiply sodium bromide by 2. So we'll actually balance everything out in one fell swoop. All right, so that is now our balanced chemical equation. Next, let's look at the net ionic equation. Now, I'm actually gonna tell you a secret. Oops, there we go. So when it comes to writing the net ionic equation, I've got a quick and dirty secret. One way you can do it is by taking the balanced chemical equation, writing a total ionic equation, looking for spectator ions and canceling them. Totally fine way to do it. But it's long, and as you've experienced, time crunch is a real issue on exams, right? So one way to save yourself a ton of time, whenever you need to write a net ionic equation, look at your balanced chemical equation and identify your precipitate. For every net ionic equation, the only product will be that precipitate. It's going to be chromium 2 carbonate. The reactants will be the anion and cation that make up that precipitate in the aqueous phase separated. So this is simply chromium 2, aqueous chromium 2 cations plus aqueous carbonate anions, and that is your net ionic equation. All right, it's fast, it's simple, it's efficient. If this trips you out a little bit, do it the long way. Break up every aqueous ionic compound, identify the spectator ions, cancel them, and you're going to get straight here. I guarantee it. All right, so that is the way that you'll see me doing it from now on, because again, being efficient during exam time is important, and I want to equip you as best as I can to perform well in that context. All right, let's do another example. Oops. There. All right, let's do another example. Let's evaluate to see if a reaction occurs between aqueous sodium hydroxide and aqueous, I don't know why I wrote a P there, iron 3 chloride. All right. We know it's going to go down, right? Sodium will grab chloride. Iron will grab hydroxide. Now we just need to figure out what those cations are and what they look like. We have sodium as a +1. Hydroxide is a -1. Iron, we don't know. It's a transition metal, right? It could be anything. Anything could be the charge. But it's paired with chloride. We know one chloride is -1. So if iron is paired with 3 -1s, it itself must have a charge of +3. All right? So sodium chloride is going to come together in a 1-to-1 ratio, NaCl. And iron 3 is going to come together with hydroxide in a 1-to-3 ratio. All right? I wrote aqueous there again. Was it a Freudian slip or just straight up wrong? Let's find out. So, lame. Oh wait, no, not lame. Okay, sweet. So, first, sodium chloride. Sodium is always soluble. So we don't even have to think about it. It's just aqueous by default. Iron, we have no idea. If you look back at the solubility rules, it says nothing about iron. The solubility rules in your book, it's exactly the same. Nothing about iron. All right. Hydroxide, however, is usually insoluble. All right. The question is, what is hydroxide soluble with? And looking back at our solubility rules, it is slightly soluble with calcium, barium, and strontium. One thing you'll notice is that iron 3 is not on this list. So that means that iron 3 hydroxide is a solid, and we do have a precipitate, which means that we will need to, balance this chemical equation and, whoops, that's not aqueous, and write the Net Ionic Equation as well. So, let's take our chemical inventory, our atomic inventory. We have sodium, oxygen, hydrogen, iron, and chlorine on both sides of this reaction. Sodium, oxygen, hydrogen, iron, and chlorine. Sodium is 1, oxygen is 1, hydrogen is 1, iron is 1. Wow. Chlorine is 3. Okay, that wrecks the curve. Sodium is 1, oxygen is 3, hydrogen is 3, iron is 1, chlorine is 1. Well, one thing that clearly needs balancing is this chlorine situation, right? We need 3 chlorines on our product side. So we're going to multiply sodium chloride by 3. This will balance chlorine and change our sodium count. Sodium will now have 3. And so now we need to come back And, lame. Oh, no, not lame. I didn't make a mistake. Sodium, you'll notice, we now have 3 on our product side, but only 1 on our reactant side. So we need to multiply sodium hydroxide by 3. This will balance sodium, balance oxygen, and shoot, even balance hydrogen in one foul swoop. So this is now our balanced chemical equation. Balanced chemical equation. Sorry, I lost my phase symbols there. Now, for the net ionic equation, remember, to write a net ionic equation, just look at your precipitate and build your net ionic equation off of your precipitate's formula. So the sole product of the net ionic equation will be iron 3 hydroxide in the solid phase. All right, and the reactants will be 1 aqueous iron 3 cation plus 3 aqueous hydroxide anions. All right, that is the net ionic equation for this precipitation reaction. All right, I have 2 more solubility rules examples. Let's see if we can get both in. The first is we're going to evaluate the reaction, or if there is a reaction, between aqueous sodium chloride and aqueous Mercury 1 acetate. Does this produce a chemical reaction, a precipitation reaction? Now this is going to pair, if it does, we'll see sodium pairing with acetate, and we will see mercury, mercury pairing with chloride. So let's take a look at our ions that we're using. So sodium is +1, chloride is -1. Mercury 1 is a polyatomic ion, Hg2, 2+. So it's Mercury 1 because each mercury inside the ion has an oxidation state of 1, but the ion itself is a polyatomic ion, and there's 2 of them, so there's a total charge of 2. Acetate is a polyatomic ion as well, with a charge of -1. So since sodium's +1 and acetate's -1, those combine in a 1-to-1 ratio. C2H3O2, some phase, plus Mercury 1 has a total charge of +2, so it will pair with 2 chloride anions, and it will be in some phase as well. All right. Now we have to determine which, whether these are soluble or insoluble. Again, actually, both sodium and acetate are always soluble. Both of them, the cation and the anion. This is a little bit of the of like a dream team here. So, aqueous. Now, Mercury 1, we don't know a ton about, but we do know that chloride is usually soluble. It's insoluble when you pair it with silver 1, mercury 1, or lead 2. And check it out. We have mercury 1. So even though chlorine is usually soluble, because we're dealing with mercury 1, that makes it insoluble. So mercury 1 chloride will be a solid. Ah! Emma, great question. I'm gonna answer it after completing this problem. So I'm gonna finish this one and then I'll come back and write that out because that deserves a little bit of board time and its own space. Okay, so because we have a precipitate in this reaction, we need to balance it and write a net ionic equation. First balancing, we need sodium, chlorine, mercury, and wow, carbon, hydrogen, and oxygen. We got 6 elements in this reaction. On our reactant side, there's 1 sodium, 1 chlorine, 2 mercury atoms, 4 carbon atoms, 6 hydrogen atoms, 4 oxygen atoms. On the product side, there's 1 sodium, 2 chlorine, 2 mercury, 2 carbon, 3 hydrogen, 2 oxygen. The first thing that jumps out to me is chloride. All right. We have 2 chlorides on the product side, only 1 on the reactant side, so I need to multiply sodium chloride by 2 to balance chlorine. This gives me 2 chlorine on each side of my reaction, but it also messes up sodium. Now I have 2 on my reactant side, only 1 sodium on my product side, so I need to multiply sodium acetate by 2. Now this is going to change 4 elements all at once, but as you'll see, as we crunch these numbers, it actually balances all of them, which is kind of awesome. Alright, so that is our balanced chemical equation. Alright, now that we have our balanced chemical equation in place, oh, lame. Here, let me erase these. There we go. Now that our balanced chemical equation is in place, we can write our net ionic equation, which is going to be based solely off of the formula for our precipitate. So the sole product of the net ionic equation will be Hg2Cl2 solid. Ah, Sarah, great question. And actually, as I write this out, there will be the answer to your question. The thing to remember here, and this is what makes this one a little tricky, which is why I wanted to do one in lecture, is this is the polyatomic ion. Oops. This is the polyatomic ion Mercury 1. All right, the polyatomic ion Mercury 1 has a chemical formula Hg2 2+. So it's literally two positive mercury ions stuck together, all right, with a total charge of +2. So that's the reason why it's there. It's not mercury 2, that would be mercury with a charge of +2. This is mercury 1, which doesn't exist by itself. It always exists with a buddy. So together, they have a charge of +2. The net ionic equation here, then you'll have to have the polyatomic ion named mercury 1 free floating plus 2 chloride anions. All right, and this is your net ionic equation. All right, so that is the reason why you don't do two Hg1s, you do Hg2 with the 2+ polyatomic ion, and then 2 chloride ions to balance that +2 charge. All right, so Emma, to answer your question, let me find. Dang, we started doing these about 20 slides ago. Let's say we had. Okay, good, Sarah. I'm so glad. Let's say I asked you to write the chemical formula for the polyatomic ion mercury 1 phosphate. All right, mercury 1 phosphate. Both of these are polyatomic ions. Mercury is a polyatomic ion that's Hg2 with a charge of 2+. Phosphate is a polyatomic ion PO4 with a charge of 3-. Now the problem is our charges here do not go into each other evenly. 2 does not go into 3 evenly. And so whenever you have that situation happen, you are going to give each ion, the cation and the anion, you're going to give the cation a subscript equal to the anion's charge and the anion a subscript equal to the cation's charge. So together, we've got our first polyatomic ion, mercury 1, and our second polyatomic ion, phosphate. The subscript for mercury 1, your cation, will be equal to your anionic charge, which is 3. The subscript for your anion will be the cationic charge, which is 1. So Emma, circling back to your question, which was, do you combine, because we have to have multiple mercury 1s, do you combine that with its subscript? So would you write this as Hg6 PO4 2? The answer is no. Whenever you're dealing with a polyatomic ion, you always keep the polyatomic ion as a discrete unit. So you throw it into parentheses, then outside of it, add however many of that polyatomic ion you have. So hopefully that makes sense, and hopefully that clears it up. All right. Now, with we have one last example. I have one last example in my stable of of predicting if a precipitation reaction occurs using solubility rules and writing the net ionic equation. So let's do it. All right, so sodium, aqueous sodium nitrate, mixing with potassium chloride, also aqueous. Let's see if a precipitation reaction occurs. And we know the drill. Sodium pairs with chloride. Potassium pairs with nitrate. let's evaluate our ions. So we have sodium, nitrate, potassium, and chloride, which means that we're going to have a 1-to-1 ratio for both sodium chloride plus potassium nitrate. And here, this one's actually a very quick study because sodium is always soluble, and so is potassium. So both of our products are aqueous, which means there's no reaction and no further action is necessary. No need to balance, and there's no Net Ionic Equation to write because no reaction has occurred. Okay. All right. Now, okay, so that is the end of precipitation reactions and solubility rules, all right? How these things will show up on exam 2 is going to be very, very similar to what you just saw. Well, let's see, we got a question. Richard, is it possible to get 2 solids on the reactant side? That is a great question, and the answer is yes. It totally is. And as a result, if you were to run into a situation like that, or I guess I should say, you don't have to be afraid of that instance coming up because you just have to follow the solubility rules. Apply the solubility rules to the first one, apply it to the second one, and then see where they come. Another thing, you'll notice I was actually deliberate in all of these problems to assigning the solubility to both things. The only way you could miss if both were solids is if you're used to just applying the solubility rules to one if you think it's a solid, and if it's a solid then you stop. You'll need to apply the solubility rules to both products, and that's how you can avoid missing a situation like that. Totally. Okay. So that is precipitation reactions, solubility rules. Again, I recommend either memorizing the solubility rules or writing them on like an equation sheet, a cheat sheet for when you're taking the exam, so you have it as quick reference, because you're definitely going to be seeing a decent chunk of these showing up on exam 2. Cool. Okay. I think I'm going to put a pin in lecture there because we kind of finished the thing, and rather than trying to start a new thing, we have 2 subjects left in chapter 4 to talk about. One is redox reactions, and the other is acid-base chemistry. Now, in the book, just as an FYI, if you're one of those humans who likes to read along or ahead of schedule, in the book, it's precipitation reactions, acid-base, then redox. But I'm going to switch the order for redox and acid-base because I think the redox stuff is harder. More students tend to struggle with it, and so I want to give us more time to go over that. I don't want that to be rushed. So if you're a human who likes to read ahead, I'm going to be doing the redox stuff next, and then coming back to the acid-base. Ludwig, great question. So Ludwig was asking, are we always looking at the product cations when using the solubility rules? And for the purpose of determining whether or not there's a precipitation reaction, you are, because a precipitation reaction, by definition, takes 2 aqueous reactants, mixes them, and then one of the products is insoluble. So if you're doing a precipitation reaction, by definition, you're starting with 2... Oh, I was a little off camera there, sorry. Starting with 2 soluble things and ending with at least 1 insoluble thing. So great question, great observation. Again, I will be seeing you all, or not all, some of you possibly in lab tonight. I'm going to do a little intro lab lecture to our second E-Lab. Drop by if you have questions or email them in. And if I don't catch you at 7, then I'll see you all after the weekend. I hope yours is awesome. Take care.